Why isn't Earth a frozen ball of ice? Based on our distance from the sun, simple math says our planet should be locked in a deep freeze. Yet life flourishes, oceans flow, forests grow, and we enjoy a mild climate. What's keeping us warm? The answer isn't in the ground, but in the thin, invisible veil above us, our atmosphere. This layer acts as Earth's thermostat, making life possible. The sun's energy warms the surface, and Earth radiates heat back into space as infrared light. If all that heat escaped, we'd freeze. Something must be trapping it. This puzzle led scientists on a journey, one that began with a mathematician fascinated by heat. He saw the planet as a grand physics problem: energy in, energy out. The key was the atmosphere, slowing the escape of heat. This wasn't solved in a single moment, but through generations of curiosity and discovery. Each scientist built on the last, piecing together the mystery of our planet's invisible blanket. This is the story of how we discovered the greenhouse effect, and how it keeps our world alive. In the 1820s, French mathematician Joseph Fourier asked, "Why is Earth so warm?" He realized the atmosphere must act like a giant pane of glass, letting sunlight in, but trapping heat. To explain, he described a hot box, a glass-top box that gets much hotter inside than the air outside. The glass lets sunlight in, but blocks heat from escaping, just like our atmosphere. Fourier didn't know which gases were responsible, but he had the concept right. He was the first to see the atmosphere as an active player in regulating temperature. His insight: it's not about blocking sunlight, but trapping outgoing heat. Fourier's idea laid the groundwork for everything that followed. He framed the problem and pointed future scientists in the right direction. The next step: moved from theory to experiment. Someone needed to test if the atmosphere really could trap heat, and which gases did the work. In the 1850s, Eunice Foote, an American scientist, ran a simple experiment. She placed thermometers in glass cylinders filled with different gases and set them in the sun. She found that cylinders with moist air got hotter than dry air. Most importantly, the cylinder with carbon dioxide got much hotter and stayed warm longer. Foote wrote, "An atmosphere of that gas would give to our Earth a high temperature." She was the first to show experimentally that carbon dioxide traps heat. Her work was overlooked for decades, but she had found a crucial piece of the puzzle. Foote's experiment was the first proof that not all gases are equal when it comes to warming the planet. Soon after, Irish physicist John Tyndall took the question further. He built sensitive instruments to measure how gases absorb heat. Tyndall found that nitrogen and oxygen, the bulk of our air, let heat pass right through. But trace gases like water vapor, methane, and carbon dioxide were powerful heat trappers. Even in tiny amounts, they acted as Earth's true thermal blanket. Tyndall's experiments proved, beyond doubt, that these trace gases keep our planet warm. He even speculated that burning coal could increase carbon dioxide and change the climate. Tyndall identified the atmosphere's most important threads. The stage was set to calculate the consequences of changing these gases. The science was now ready for the next leap. In Sweden, Svante Arrhenius took the next step. He wondered, if you change the amount of CO2 in the air, how much does the temperature change? Arrhenius spent months calculating, by hand, the effect of halving or doubling CO2. In 1896, he published his results. Halving CO2 could trigger an ice age. Doubling it could raise global temperatures by 5 to 6 degrees Celsius. He saw this as a possible benefit, not foreseeing today's concerns. Arrhenius was the first to link industrial emissions to global warming with real numbers. He turned theory and experiment into a predictive model. Around the same time, the term greenhouse effect was coined. The science was now clear: small changes in CO2 could have huge impacts. The greenhouse effect was no longer just a theory, it was a measurable reality. The foundation for understanding climate change was set. This story is a relay of discovery: Fourier's theory, Foote's experiment, Tyndall's proof, Arrhenius's calculations, each built on the last, revealing how our atmosphere keeps Earth habitable. Their work underpins our understanding of climate change today. They showed that our climate is dynamic, sensitive to even small changes in atmospheric gases. Thanks to them, we know that adding carbon dioxide changes our world. This isn't politics, it's physics, proven over centuries. Their legacy is knowledge, the power to understand and protect our only home. The greenhouse effect is why we're here, and why our choices matter. The story continues, as we decide what happens next.